This is a review of confidence intervals. So we start with what we call a point estimate. So like we use the sample mean x bar as an estimate of the population mean mu, and because x bar is just one number or a single point, we call it a point estimate. But that doesn't capture as much information as we really want to, so we're going to come up with a confidence interval. So for this example, we want to estimate the true mean height mu of NBA players in 2001 to 2002. So we decided to take a sample of 10 basketball players and find their sample mean height x bar. We found the sample heights, there they are. The sample mean height is 79 inches. So our estimate of the population mean height is 79 inches. But do we really have any guarantee that our population mean height is 79 inches? Well, it's probably really not even exactly 79 inches. Because if I took a different sample, could I get a different sample mean height? Yes, of course, because remember, every different sample is going to give you a different sample mean. So I could take another sample of 10 NBA players and find their heights, and they have a different sample mean of 77.5. So now our best estimate would be 77.5. But you might be saying, like, one person got 77, one person got 79. How does that make any sense? So if every different sample gives us a different sample mean, that means every different sample gives a different estimate of the population mean. So what we want to do is be able to combine some of this variability into a confidence interval. So a confidence interval for the population mean is an interval constructed around the sample mean so that we're very sure or confident that this interval contains the population mean. So for one sample t confidence interval for a population mean, it's going to be x bar plus or minus t star times s over the square root of n. So t star is what we're going to call a critical point. That comes from the t table. S is our sample standard deviation, n is our sample size. So notice I like to do t star as the critical point. A lot of textbooks will use some more technical notation. The reason I like to do t star is I like to think about it more logically and graphically than trying to memorize formulas. If you were going to look at on the textbook, they probably say it's going to be t alpha over 2, comma, n minus 1. That alpha minus 2 is telling us how much area should be in the tail. But again, I don't like to memorize that. I just like to draw a picture. So we have t alpha over 2, n minus 1. What that means is you want to find a t value that has alpha over 2 area in this tail. The reason why is we'll put alpha over 2 in each tail, and then in the middle we have 1, not 100. We have 1 minus alpha in the middle. That means if you have something that looks like a 95% confidence interval, we'll put 0.95 in the middle, and then, because that's 1 minus alpha, that tells us that alpha equals 0.05, and if we do alpha over 2, that's 0.025. So that means we have 0.025 in this tail, 0.025 in this tail, and this is our t of 0.025 and n minus 1 degrees of freedom. So that's what the notation means. I just draw a picture every time instead of worrying about that notation. Let's see how that works in our example. So we want to estimate the true population mean height of our basketball players. Let's use our same old sample. We have our sample heights, our sample mean, our sample standard deviation. Let's find a 95% confidence interval. So our formula is x bar plus or minus t star times s over the square root of n. First thing I'm going to need to know is my critical point, my t star. So we're going to go to our guided notes on page 306 to look at a t-table. We also need to know our degrees of freedom before we get too far. So our degrees of freedom are supposed to be n minus 1. So our sample size is 10, so we'll do 10 minus 1 equals 9. We're going to draw our picture. We want a 95% confidence interval, so that means I start with 95% in the middle, or 0.95. And then if I subtract that from 1, because everything has to add up to 1, that means I have 5% for each tail. But I have 2 tails, so let's divide it by 2. So 0.05 divided by 2 means 0.025 in this tail, 0.025 in that tail, and I'm looking for this t star value. So 9 degrees of freedom, we're looking for 0.025 in the tail. So I go to the t table, I have 9 degrees of freedom, 0.025, that's 2.262. Okay, now we can plug it all in. We have 79 plus or minus 2.262 times our sample standard deviation of 3.5 over the square root of 10. And this should give me about 76.5 to 81.5. So that's my confidence interval. Anytime we ever write a confidence interval, though, if you've taken any of my classes especially, we will always write an interpretation for it. So we'd say something like, we are 95% confident. So 95% confident that the true population mean height is between 76.5 and 81.5. Oops, 5. So that's our interpretation of our confidence interval. Now, in this one specific case, I have the data set with the heights of all the players, and I found the population mean height is 79.14 inches. We don't normally have that, but I do for this one case. So again, in practice, you won't know it, but since we do for this one, did our confidence interval contain the population mean mu? So is 79.14 in our interval from 76.5 to 81.5? Yes. But in practice, since you don't know the population mean mu, there's no way to tell whether or not your interval actually contains the population mean mu. So let's look at what confidence intervals mean and how that would affect us. So again, because I have the data set for all the players, I can take a different sample and find the 95% confidence interval many times. So I put my results from the first 10 samples in a table and then graphically displayed the rest of them. So if I got a sample mean of 79.7, I got this confidence interval from 77.5 to 81.9. So did it contain mu? Let's write ourselves a note. Mu was 79.14. So this one did. So yes. Let's see, my next one, yes. The next one, yes. 77.82, yes. Oh, but look, this one only goes to 78.8. So this one's going to be a no. And then yes, and I think all the rest were yes. You can see graphically how I put it on. See, the red ones are the ones that don't contain it. So like here, here. So we have these different red ones where our sample mean was just kind of off in the tails, just high enough or low enough that it didn't actually contain our population mean. So did all of them contain it? No. How many did? If you count it up, there were 94 out of 100 that contained mu, our population mean. And you might think, oh, well, that's like 94%. It was a 95% confidence interval. That's because we only took a few of them. If we actually took like hundreds or thousands of samples, then we would actually find that 95% of them contain the population mean mu. So if we took millions of samples, 95% of the confidence intervals would contain the population mean mu. There's no way to tell if our sample is one of those good, accurate 95% of the samples or the unlucky 5%. But because we know that we'll be right 95% of the time, we feel comfortable using these results and hoping that we're probably accurate. So we have another applet that we can go look at quickly. Okay, so in this one, we're taking a sample and finding confidence interval. It doesn't really matter what our mean and standard deviation were, but we are taking sample size of 1,000. So we could take one sample. Notice this is the actual data of the 100 data points up here. So that's the actual data. Then this is our sample mean down here in the red. And this is our confidence interval. So you can see on this one, we were unlucky. The first sample we picked had a sample mean that was just low enough that the confidence interval doesn't quite contain the actual population mean. Let's try again. So I get a different sample mean, and now my confidence interval does contain it. Let's see what happens if I try 100 samples. You'll see that this 100 samples, we get different sample means. So these are all of our different sample means. Notice that the possible sample means kind of look like the normal distribution. But occasionally we get a sample mean that was really far off in the tails, as evidenced by these red blocks. And if your sample mean happened to be in the tails of all of those possible sample means, then your confidence interval is too far away to actually contain the population mean. Let's see what happens if we look at 1,000. Notice it looks even more like the normal curve, and you can just kind of see those red ones out here in the tails. Those are the ones where if we're unlucky enough to get a sample mean that was really far in the tails of the possible sample means, then our confidence interval doesn't actually contain the population mean mu. And just one warning, because this is one of the most often repeated mistakes in statistics. So we found the population, or the confidence interval for the population mean is 76.5 to 81.5. This does not mean that the probability is 0.95 that the true mean is between those two numbers. Okay, don't ever say that. That doesn't work in statistics. The reason why is that our true mean is a fixed value. It's not random, it's not changing, at least in the way we think about statistics. And so it doesn't make sense to talk about the probability of the value mu. So instead, it's our interval that's changing based on which sample we choose. So the 95% is how often our confidence intervals actually contain the population mean mu.